All right. So you can see that here we have part one, right? It's elementary graph algorithms. And after these, I think we will spend a week, more than a week actually. I think 3 lectures, including this one, hopefully, to cover these elementary algorithms. And we will first, of course, introduce the basics, like what a graph data structure is, how it is defined. And I think we had some ideas about what a graph look like, right? When we talk about the disjoint sets, right? A disjoint sets like is a collection of vertices in the graph. So today we will see what a vertex is and how we can connect two vertices to create an edge, and how the collection of both vertices and the edges are called a graph altogether. Okay, so this chapter, including this one, the basic graph algorithms, and the next one, the more advanced graph algorithms, they will be the main focus for the rest of this semester, and it will be the focus for the final exams as well. Okay, final exam as well. So yeah, it's actually the problems that we will introduce using graph data structure are actually very practical problems, like the navigation problem. How do you, if you think of a map that you are using on your cell phone, right? You want to navigate from your starting location to a destination point, then it's a very typical routing problem, or path-finding problem. So you want to start from one vertex in a graph, and given another vertex, how do you find the shortest path, right? So these are very typical problems that should be solved with a graph data structure. Okay, and the graphs we can actually, the data structure do more than that than finding a path on the map. Actually, yeah, we will see that a lot of more abstract problems can also quite related to the graph. Okay, so let's first have an overview of the topic. Okay, so it's basically everywhere in computer science, in the field, in the discipline. So for example, we can represent like the circuit network, the physical network, the internet, social networks, and even in dictionary, in knowledge base, all these data structures, all these knowledge can be represented using a graph approach, using the graph concepts. Okay, and the key concepts of using a graph is vertices, edges, and weights, and also other more attributes, for example. But the keys are the 3 components here. You need to have vertices and the edges that connect the vertices, and the weights that are associated with the edges. Okay, so we will look at typical algorithms on how to search a graph. Okay, so there are 2 types of graph searching algorithms. So including the breadth first BFS and the depth first search. Okay, and the purpose of a searching algorithm is that you start from one point in a graph, and then you wish to go through all the vertices or all the edges, right? So you want to visit all the possible vertices in a graph, and that will require some smart design that keep track of the path you have visited, and you need to have a good strategy. For example, you can visit the most nearby vertices, right? And you after you have done that, you take a step further, right? Approaching take one more step towards the unvisited vertices, right? So that is the one strategy, and of course you can take other strategies. So that is the first type of algorithms that we will talk about here. And more advanced algorithms, like if the edges in the graph, they have weights, then a typical problem, such as like spanning tree problem, is the algorithm that we need to take into consideration all of the weights that connects all the vertices. Okay, so connectivity in this case is the secondary factor, right? When we are considering how to build a tree that connects all the vertices in the graph, we are also interested in not just about whether all the vertices are covered, but we are also interested in at which cost we are connecting all the vertices. Right? Some solutions may come with a greater cost, and then we wish to minimize that cost. Okay, so this is apparently a more complex problem than simply to search a graph. Okay, and lastly, I think we mentioned it before, right? How to find the shortest path between vertices, and that is also a example of the advanced graph algorithms we will talk about in this lecture, in this chapter. Okay, but we will start from the simple algorithms to start off. Okay. Anyway, so let's look at first how to represent a graph or graphs. Okay, so we can use the capital letter G. That is our convention throughout this chapter. We use that G to represent a graph that consists of a set of vertices. So this capital V is the set of vertices, okay? And also the third capital letter E, which is the set of edges. These are very straightforward definitions, right? So an edge is the one that connects a pair of vertices, okay? An edge is like a line that has two ends, and at each end there is a vertex, okay? So that is a very straightforward concept. And the convention we take is to use this equation, like G equals V of E, to indicate that, okay, in this graph G, we have a set V and a set E that includes all the vertices and the edges in the graph. So, for example, if we use the integer number 1 to 5 to indicate, to represent all the vertices in this graph, and all the lowercase letters to indicate the edges, then this graph can be represented by these two sets of vertices and edges. Okay, so the capital V is the numbers from 1 to 5, and the set E is the lowercase letter from A to G. Okay, and we can write them together as the collection of both V and E represents the whole thing here. Okay, that is the so-called graph data structure. Okay, so since V and E are sets. Okay, so they are very similar to the mathematical sets. Okay, so there shouldn't be there's no duplicates elements in the sets. Okay, so if we can use the put two vertical bars, which is the size of the set V to indicate the number of vertices, and the size of E is the number of edges. Okay, and a simple mathematical rule is that the number of edges should be bounded the number of vertices square raised to power, that is raised to power of 2, right? So this is a principle that is I think it's easy to understand. Like if you put all the vertices, for example, into a column here, right? And if the question is that you want to enumerate all the possible edges in this graph, what you can do is that first you can index all the vertices here. Let's say this is 1, 2, 3, 4, right, until let's say V, all right? And what we can do is to copy this column, put it into a second column, right? It's the same vertices here from 1, 2, 3, 4 until V, right? Put a number here. Okay. So the question actually becomes how many possible connections there could be between these two ends of an edge, right? So if you want to create an edge, it could be from 1 to 2, right? That is an edge, right? And also it could be from 1 to 1. So that is a special case. It's like within the graph, for example, if I start from here and then going back to itself, that forms a circle, right? Let me use a eraser. So if an edge starts from vertex 1 and goes back to vertex 1, then it's also a valid edge, right? Because the two ends are the same vertex. Okay, so in that case, this also counts as an edge. Okay, so another case that look at the two columns is that we can start from 2 and ends at 1. Okay, so you may see that this is also so I see the question that is there any practical use for one of those? Yeah, I think there's a pretty practical usage for the circular edge, like it's connecting to itself. So for example, we want to define a procedure, like we want to use the vertex to represent a particular step within the procedure, right? So in one step, we want to keep the possibility that we will stay in the same step, right? So that's it's like yeah, well, it's like defining the procedures of doing some complex tasks. Okay, so sometimes the same step needs to be visited several times, right? So just based on the areas V and E, how are we supposed to derive the figure? Yeah, so that is a good point, actually. With only the V and E's, that is not sufficient to like construct or reconstruct the structure of the graph, because we don't have connectivity information just within these two areas. We will need to know, like for each edge, what are the two connecting vertices, right? So let me finish this slide. We will look into that immediately. Okay. So I just mentioned that, right? We have one edge from 1 to 2, right? And we can also have another edge that is from 2 to 1, right? So it looks like a duplicate, right? So, but that may not be two identical edge if we care about the direction of the edge, right? If we differentiate two directions, like we can say the edge from 1 to 2, right? If we put an arrow into that edge, then it is a different edge from the edge that points from 2 to 1, right? So these two edges with arrows, they are directed edges, right? So what I want to show with these two columns here is that if you look at the left end of an edge, it has V possibilities. There's V edges to choose from, okay? And so, and for the right end, the right vertex, there are also V possibilities to choose from, right? So the total number of possible edges with V vertices in the channel, in the graph, is V times V, right? So that is the V raised to the power of 2. That is where this quantity is from. Okay, so basically this can be used to, that is a basic principle that any graph should follow, right? So if you look at, so if you find an edge data structure that's the number of edges is greater than this quantity, then there's a problem in the definition of the data structure. Okay, so yeah, that's the basic representations for graphs. Okay, then it comes to the directed and undirected graphs, right? These are easy to understand. Like if we have arrows on the edges, if the edges have directions, then the whole graph is called directed graph. And or if all the edges don't have directions, then it's simply called undirected graphs. Okay, so that's some concepts on the edges. And the next concept is the weights. Okay, if we are talking about some weighted graphs, then we are actually referring to the fact that each edge has a number, has an associated number. Okay, so so this number can be described by this weight function, right? It's a one-to-one mapping function. Like we given an edge, we should output some real number. Okay, so these the weights on the graph. Like now, if we look at this example, we have now two types of integer numbers. Okay, so the numbers within this circle, they are the index for the vertices. Okay, so the one here means that this is the vertex 1, vertex 2, right, vertex 3. So these are not the magnitudes. They don't have magnitude meanings, all right? But the numbers associated with the edges here, like the 7 here, the 8 here, the 11, the 9, they are the weights, which means they represent the magnitudes, right? They have their magnitudes have meanings. Like if you think of these weights as the distance between two cities, right? Then you can say that the distance between city 1 and city 2, right? It takes maybe 7 hours to travel, right? So these numbers have these specific meanings. could be different meanings. Okay, and these weights can sometimes be not just the integer numbers, but it also could be float numbers, and also even could be negative. Okay, that depends on what type of actual problem that the graph data structure is describing, right? Say, if we describe a map of or the flight routes between airports, then if it's the flighting time that we want to describe, use the weights, then it is impossible to be negative, right? But if it's another problem, say if we want to describe how much money to transfer between bank accounts, right, or digital currency, cryptocurrency between different accounts, then the weights can possibly be negative values. Like the in and out direction can be described by the positive versus negative values, right? So we will have some experience with the negative weight graphs in the future. Okay. All right, then it comes to one of the questions that I have seen in the chats. Okay, it's like, how do we represent the graphs so that we can reconstruct from the two areas of vertex and edges? So we basically have two common ways. The first one is called adjacency lists. Okay, so I hope you can focus on this, like realize it's a plural form. Okay, so it's actually a bunch of lists. It's not just one list. Okay, or we can use something called adjacency matrix. Okay, so these are two different methods. Okay, so they are suitable for different types of graphs. Like if you have a sparse graph, that's you have more vertices relative to the fewer numbers of edges, then the agency list would be more efficient. And in other case, if you have a lot of connections, a lot of edges between the vertices, then it's more efficient to use the dense graph, to use the adjacency matrix. So we'll start from the adjacency list here. Okay. So yeah, that's a good question. Is there a threshold between? So actually, no. So that depends. That really depends on the actual needs and how tolerant you are to resources. Okay, so if you prefer to like use adjacency list, even though it's a dense graph, that is also okay. That will just cost you a lot of memory. Okay, but I would say for most of the algorithms that we are gonna implement in this lecture are basically using the adjacency lists, because this way of representing the graph is more straightforward. I think it's just closer to the way that human minds visualize the vertices connecting to each other. It is just closer to the how human minds process those connecting vertices. Yeah, so that is my experience. Okay, so but I think it will be useful if we are aware of another way of representing the graph using matrices, okay, which also makes sense. Yeah. Okay. So the data structure here is a typical linked list. Okay, so it's like the node here in the middle. It has two components. The first cell is some value of it, and then the next cell is a pointer that points to the next one, right? So it's like it links to the next elements in the list. Okay, so this is a typical visualization of the linked list data structure. Okay, so if we're gonna represent a graph using adjacency lists, so we will have, first of all, we will have an array. Okay, so this array, let's call it ADJ to as a short form for adjacency. Okay, and this array actually consists of that many lists. Okay, okay. So because it has V lists, so each list actually corresponds to each vertex in V. Okay, so for each vertex, the adjacency list can be accessed by using these index between the square box, or wheel between the square parentheses. Okay, we can use the ADJ of U to contain all the vertices V, such that there is an edge connecting U and V. Okay, so another way of saying this is that for the edge, for each vertex U, if we go to the ADJ of U, it actually includes all the other vertices that connects to U. Okay, so it's all the neighbors. Okay, all the neighboring vertices are contained in this list. Okay, so that's where the name adjacency comes from, right? It's the records all the adjacent vertices for each node in the graph. So there's little difference between a directed graph and an undirected graph. Like we have a first look at this graph with no directions, right? And the adjacency lists is stored in these attributes. And the first one is adjacency list for the vertex 1. Since we know that 1 connects to 2 and 1 also connects to 5, right? There are 2 edges. So this list has such many elements in it. It has 2 and 5, right? And actually the order, the sequence 2 or 5, which comes before, is not a fixed, right? Unless you have specified some rules to define the order, right? But in this case, it doesn't make a huge difference if you put 5 before 2, right? And for another, if we look at another vertex, which is, say, the vertex 2, right? So the vertex 2 has 1, 2, 3, 4 edges, which connects to 1, 5, 4, and 3. So this 1, 5, 4, 3 should be listed in the adjacency list of vertex 2. Okay, so indeed 1, 5, 3, and 4 are listed. So you see the 3 comes before 4, but that doesn't really matter in this case. Okay. All right, and let's look at a different example using this directed graph. Okay, so the graph is directed, which means we have arrows in it. And if you look at, again, let's look at the vertex 2 now. Okay, so the directed graph has a constraint on the graph, on the edges. So we need to start from the an edge is defined by a starting edge, a starting vertex, and an ending vertex. So if you look at 2, so there seems to be like 3 edges, okay, connected to 2, okay, but the adjacency list for 2 only stores 5 in it, okay, because it only has one edge that leaves the vertex 2, right? It has only one edge that leaves from 2 to other vertex 5 because of the definition, okay? Because the definition of the adjacency list is the all the vertices such that the edge starting from U and ends at V exists in E, okay? So in the graph here, we only have the edge from 1 to 2, but we don't have the edge from 2 to 1, right? So that's why the 1 and 4, they don't exist in the adjacency list for the vertex 2, right? So you can see that this is a little bit difference depending on whether the edges are directed or not directed. Okay, so let's look at some properties of adjacency lists. Okay, so first, if the graph is a directed graph, which means it has arrows, it has directions, then the summation, the sum of the length of all adjacency lists is the number of edges. Okay, so it's the same example from the previous page. We can simply count this. Okay, the first the first adjacency list for vertex 1, it has 2 elements, right? So that is 2. So we sum up all these lengths of all adjacency lists. That will give us 8. Yeah. Oh, I see the question. Thank you, Catherine, for answering this. So the summation is 8, right? And if you count the numbers, right? 1, 2, 3, 4, 5, 6, 7, 8. Indeed, right? There are 8 edges. So this is a useful property, right? Whenever you want to you can use this to estimate. You can use this property to estimate the running time efficiencies for some algorithms, right? So if you have gone through all the adjacency lists, for example, in one pass, then that basically means that you need to visit all the edges once. Okay, so it's shows the it is pretty good estimates of running time complexity for some algorithms. Okay, and if it's undirected graph, so we can guess that the summation of all the agency lists is then now 2 times the number of edges, because from the previous slide we can see that the length of the undirected graph is apparently longer. Okay, so that is the same example here, and we can see that if we sum up the length for all the lists together, it is 14, which is twice the number of edges. And the reason why is that because the edges don't have directions, so it's basically counted twice, right? If you look at 1, then the 2 is included, and if you look at 2, the 1 is also included, right? So it's like we have counted all the edges twice within this adjacency lists. Okay. All right. So the next second adjacency representation, second way to represent the graph is to use adjacency matrix. Okay. So these methods, we need to allocate, or we need to create a matrix that is in V times EV space. Okay, so that matrix needs to consist of V times V elements to represent the connecting relationship between all the all vertex pairs. Okay, and we will use the entry in that matrix to represent whether 2 vertices are connected to each other. Okay, say if the vertex from I to J exists in is one of the edges, then we will let that entry to be 1. Other case, it could be 0. Okay, so you can see the example for a simple graph on the left can be represented by a matrix from in the right. So the zeros, because there's a connection between 1, 2. There's a 1 here, right? There's a 1, 5 here, so there's a 1 here. Okay, so all the elements are, all the entries are 0 because the 1 don't connect to 4 or 3 or 1 itself. Okay, and the directed graph, it's I think it's even more sparse if you look at the matrix. And you can see that from 1 to 2 and 1 to 4. So the 2 1s are here, right? And if you look at 6 to 6, so there's only 1 here. So a difference like between these 2 matrices that you can see that is that if the graph is undirected, then if you look at the matrix, if you split the matrix by the diagonal line, then it's symmetric, right? Symmetric distribution of 1s along this diagonal line. But for the directed graph, it is not the case, right? That is basically because the arrow, the edges from from the starting vertex to the ending vertex is considered as an edge, but not the other way around, right? But for the undirected edge, the same edge is counted twice, right? The same connectivity is counted twice. Okay. All right. So that's pretty much for how to represent a basic graph data structure. Okay, and I think I will end the class here. So we'll not go too deep into the searching algorithms. These will be the parts that we will start after the the second midterm. And also, I think there will be no quiz question for today, and we will continue to talk about the graph algorithms I think today we have laid out all the basics for that part. And for the next Thursday, we will start talking about searching algorithms, including breadth first and search and depth first search. Okay, and hopefully you can find the slides for the review for the second midterm on Canvas. I hope you have time to prepare for the second midterm. Okay. If there's no